Hello Math 122. This is the fourth and final video for chapter 4 that I'm producing for you, and today we are talking about profit, cost, and revenue, and in particular how these three different functions can be interpreted with the tools that we've developed over chapter 4 so far. So before we get going, it'd be good to review these different business functions that are going to show up in the lesson for today. All of these business functions are functions that you've seen before, but I thought it'd be good to remind you of them. So the first one is the cost function, which we denote by C of Q, and this function takes the quantity of product that's being produced as an input and outputs the cost C to produce that number of items, so Q items. The revenue function, denoted R of Q, again takes the quantity of a product that you're producing as an input, and this time it outputs the revenue that the function or that the company is making from selling that many items, so Q items. And the profit function is defined to be the difference between the revenue function defined above and the cost function defined above. The marginal cost function is defined to be the derivative of the cost function that we just defined, and the marginal revenue function is defined to be the derivative of the revenue function. So all of these things should be review. Hopefully you're very familiar with them, but these are going to be the main topics of discussion today, so I thought I'd just list them there for convenience. Ultimately, businesses are seeking to maximize profit, so they want to sell enough products to make as much money as possible. This is kind of the goal of the business at the end of the day. And from section 4.3, we develop tools that allow us to maximize functions generally. So maximizing profit in business is really just one particular application of these general methods that we developed in the last section to find global maximums on arbitrary functions. And to do so, we're going to take the profit function and we're going to maximize that function or find the global maximum on the profit function using the same method that we did in the last section. So just to remind you of the method that we used, at least to find global maximums on closed domains. So remember that closed domains are domains that include the endpoints. So let f be some function with a domain that includes the endpoints. To find the global maximum of f, we do three different things. So the first thing we do is we find all of the critical points of that function f, whatever it happens to be. The second thing we do is determine the values of the function at all of the critical points that I found from step 1. And remember, you also have to check the value of the function at the endpoints of the interval, because in this case, our interval includes endpoints. And finally, we sort through all of these values that we got from the previous step, and the largest value from that previous step is always going to be the global maximum. And I don't list it here, but the smallest value or least value from that previous step is always going to be the global minimum. Okay, so let's take this idea and let's see if we can apply it to profit functions in particular and see if anything interesting pops out. So remember that the profit function, which we denote pi of q, is equal to the revenue minus the cost. And let's say we want to maximize this function. So if we take the first derivative of the profit function, then we end up with marginal profit, and marginal profit is just equal to the marginal revenue minus the marginal cost. And if we take the derivative of the profit function, so we take marginal profit and set it equal to 0 to find the critical points, then you end up with this expression over here. So finding the critical points of the profit function is the same as asking for the points where the marginal revenue is equal to the marginal cost. So I listed that here because it's kind of an important observation that's particular about this profit function. When we're looking at profit functions, the critical points occur precisely at the points where marginal profit is equal to 0. So this is kind of the classic definition of a critical point that we gave in the last section. And for profit functions, this happens to be the same points where marginal revenue is equal to marginal cost. Okay, so how can we visualize some of these things that are going on? Well, I have a graph here, and in the graph, I have a cost function, which is in red, and I have a revenue function in blue. Let's see if we can interpret what the profit function means, and if we can interpret where I can look for the maximal profit between these two functions here. So the profit at some particular quantity Q can be thought of as the difference between the revenue function showing up on the coordinate plane here and the cost function. So maybe I'll draw an example of that. Let's say at Q equals 1, I want to see what the profit is going to be. Well, I'm going to look at the distance between the cost function and the revenue function. And in this case, the profit is actually going to be negative because the cost function is bigger than the revenue function. So hopefully this idea is familiar to you. You've seen it before. And this is exactly what I say here. So when the cost function is bigger than the revenue function, the profit is always going to be negative because profit is revenue minus cost. And when revenue is bigger than cost, the profit is always going to be positive. But we're always thinking about profit as the distance between the cost function and the revenue function. Sometimes it's negative, sometimes it's positive. So the profit is maximized when the distance between the graphs of the revenue function and the cost function is as big as possible. So you might be saying, well, it looks like the distance is as big as possible at x equals 1, where I drew before. But you have to be careful here. We're looking for where the distance is biggest, and revenue has to be bigger than cost. So this gap that I found right here, cost is bigger than revenue, so the profit is actually really, really small. Instead, I want to find the biggest gap where revenue is bigger than cost, and that occurs somewhere over here, something like Q equals 3. And it's important to note here, so remember from the last slide that the critical points of the profit function are the points where marginal cost is equal to marginal revenue. Well, if I look at this critical point that I just found at Q equals 3 in the graph here, notice that if I look at the tangent line of the revenue function and I look at the tangent line of the cost function, I wish I could draw that better, sorry about that. But if I look at these two tangent lines and you think about it, the tangent lines are parallel to one another, which tells me that the marginal cost at Q equals 3 is equal to the marginal revenue at Q equals 3, which is exactly what we found from the previous slide. Okay, so we'll close out the video with a couple of examples here. The first example, we're going to be maximizing profit, and in this case, our function is defined over a closed interval. So we'll use that method over closed intervals that we had before. All right, so I'll read the problem for you. Find the quantity which maximizes profit if the total revenue and total cost in dollars are given by, and here's the revenue function, R of Q equals 5Q minus 0.003 Q squared, and the cost function C of Q is 300 plus 1.1 Q. And again, we're looking over a closed interval here. So Q is between 0 and 1,000 units. And that allows us to use the method for finding global maximums over closed intervals as opposed to non-closed intervals. All right, so let's start off by writing down what the profit function is. So the profit is revenue minus cost. And if you take the particular functions in our case here and you subtract them from one another, you end up with negative 0.003 Q squared plus 3.9 Q minus 300. From here, we're looking to find critical points, and on the way to finding critical points, we need to take the first derivative. So the first derivative of the profit function gives me negative 0.006q plus 3.9. And now to find the critical points, we take that first derivative and we set it equal to 0. So negative 0.006q plus 3.9 is equal to 0. And now I'm going to solve for q, and I end up with exactly one critical point at q equals 650. Okay, from here, I take my critical point. In this case, I only have one of them. And I take the endpoints of the interval that I'm looking at, so that's 0 and 1,000. And I take those 3 points and plug them into my profit function pi, which I'm doing down here. And I see what the output is at each of those 3 points. So at q equals 0, I have an output of negative 300. At q equals 1,000, I have an output of 600. And at q equals 650, I have an output of 967.5. And to find the global maximum, or the maximal possible profit that I can have, dependent on q, I'm going to pick the biggest value from these 3. So in this case, that value occurs at Q equals 650. So we conclude that we have a maximum profit of $967.50, and this happens when we produce 650 items. So if a business wanted to maximize profit, they could go through this process and figure out exactly how many items they need to produce to make as much money as possible. Also, note that this step here, the previous step, gives us the minimum possible profit as well, and the minimum possible profit is negative $300, and this is the profit that the company would get if they produced no items at all. So if they don't produce anything, they're at a $300 deficit. Okay, and here's the last example. This example is a little bit different because in this example, the company that we're looking at doesn't actually have any cost. They only have revenue, and so if you want to maximize profit, it's really equivalent to just maximizing revenue. So we're going to look at how to maximize revenue, but this isn't some kind of revolutionary new idea. We're still going to use the same process where we take the function, find critical points, and then look for the global maximum. All right, so I'll read the example for you. At a price of $80 for a day trip, a whitewater rafting company attracts 300 customers. Every $5 decrease in the price attracts an additional 30 customers, and there's three things that we want to do. The first thing we want to do is find the demand equation. The second thing is to express the revenue function as a function of price. And the third thing is to figure out what price the company should charge to make revenue as big as possible. So we're going to find that revenue function from the second step, and then in the third step, we're going to take the revenue function and we're going to find the global maximum. We're going to maximize it. All right, so we'll start by finding the demand equation. Remember that the demand equation is the equation relating the quantity of the product that you're selling and the price at which you're marking the product. So in this case, the demand equation is going to be linear. I know it's linear because of this phrase right here. Every $5 decrease in price attracts an additional 30 customers. So this tells me that the slope of my function is going to be constant, and in particular, the slope is equal to -6, because every $5 decrease in the price is going to add an additional 30 customers. And if you want to, you can pause the video there and just convince yourself that this actually tells me the slope of my line has to be -6. But I have more information from the problem that's given to me. I also have that this linear demand equation contains the point 80, 300, because I know when the price is $80 for a day trip, the rafting company attracts 300 customers. So the input here is price, the output is the number of customers, and I get this point 80, 300. All right, so here's the demand equation. I have Q minus 300 equals -6 times P minus 80. So where am I getting this equation right here? This is just point slope form of a line. So I just said that the demand equation is linear and it contains this point 80, 300, and it has a slope of -6. And so I take those pieces of information and I just plug them into the point slope form of a line. So if you need to review that, again, just pause the video and go look up the formula for point slope form of a line, and you'll find that this is what you would get. And from here, you can take that point slope form and solve for Q, and now we're taking the line and putting it into slope intercept form, where the output is Q and the input is P, the price. All right, so we have our demand equation. That answers the first part. Now we want to take our revenue function and write it as a function of price. So remember that revenue is equal to the price that we're marking our product at times the quantity of products that we're selling. So R equals P times Q. But up above, we found a relationship between the quantity that we're selling and the price we're marking it at. So we can use that to substitute in for Q in this expression for revenue. And we get that revenue as a function of price is equal to P times the quantity -6P plus 780. And we can expand that and get -6P squared plus 780P. So that answered the second part of the question. And now finally, what price should the company charge to maximize revenue? So we're going to take that revenue function that we found and we're going to find the global maximum. So to find the global maximum, we start by finding the first derivative of the revenue function. And we get negative 12 times p plus 780. Now we take the first derivative and we set it equal to 0 to find our critical points. And this gives us p equals 65. And now finally, we have to be a little bit careful here. So we're looking at the revenue function, but we're not told what the domain is. So the domain, we can't assume, is a closed interval that includes its endpoints. So we're going to have to think a little bit more carefully to justify why the global maximum is occurring when the price is 65. So here's my attempt to justify to you why that is. One thing we could do is take the revenue function r of p that we already found and just graph it and look at the graph and say, oh yeah, the global maximum does occur when the price is equal to 65. And that would be perfectly acceptable. Or if I'm too tired or lazy to graph the function, I can notice that this revenue function, negative 6p squared plus 780p, is a parabola. And I know that the parabola has to open downwards because the leading coefficient inside of the equation for the parabola is negative. So it opens downward. And that tells me that this one critical point that I'm finding has to be the point at the top of the parabola up here. And so I know that that point that I found at p equals 65 has to be a global maximum. So I can conclude the global maximum occurs when the price is $65. This is the price where the revenue is maximized, and this is the price where the company should price their day trips to make sure they make as much money as possible. Okay, so ultimately this video is just one particular application of finding global maximums and global minimums, which we talked about in the last video, and this ends chapter 4. So all of the homework for you is up on Wiley Plus. You can access it now, and the quiz for chapter 4 will be up shortly.